Start. Good morning, everyone, and welcome to LMPL 2025. My name is Jun Sun, and I'm very excited to kick things off. And this is the first LMPL workshop, the international workshop on programming language and language models. So the first question here we want to ask is why we want to have this workshop. As we all know, language model is changing the world. It also changes how we write and reasoning about the code. They can help with coding, testing, and design. But they also have their very unique challenges, such as hallucinations, such as high cost, and the short context windows. All of these problems can get in the way of real-world practical deployment. So today, we want to bring together the LM language model communities and the programming language communities together to look at what works well, what breaks, and how to fix it for this inevitable marriage. Our goal is very simple. We try to share good ideas, we try to show early results, and we want to discuss with each other. And we also try to connect the research and the industry to put the good, interesting research ideas into practical, useful tools. So in this workshop, please feel free to ask questions, but please keep them short so that the speaker will have time to answer that. And also, please be kind in discussions, since we will follow the conference code of conduct. And before we start, I want to thank for our speaker, our reviewer, and organizers to make all of those things happen. And also, I want to thank all of you to come here to take these workshops. And for now, it's my great pleasure to introduce our keynote speaker, Professor Jun Sun from Singapore Management Universities. His talk is about AI safety through programming, and he will discuss how concepts such as specification, verification, and semantics can be reinvented for AI-based assistance. Please join me in welcoming Professor Sun.
Can I have my slides there? Right. It's coming up. Can I have a full screen? All right. Yep. Thank you. So thanks for having me. And then, it's my pleasure to be here. And then I do believe this is a topic that we ought to discuss a bit more. All right. So let me put up a first slide just to say where I stand on this issue of programming versus a large language model. So in my mind, at least, you may not agree that all of these are basically models, no matter it's logic or large language model, etc. All of them fits in. Should be. It's not working. Maybe I can hold on to the handheld one. Is it better? Yep. All right. So let me just say this is what I have in my mind. Sort of try to understand all this spectrum of all of these techniques that we may be using to develop computer systems. All right, ranging all the way from simple logic, programming to large language models. In my mind, they're only different in terms of the size of the model. I would consider all of these models before programming, including programming, to be small models. Beyond that, large models. And then the difference in my mind is that all of these small models, we can have some kind of capability of understanding what they are doing and then we sort of believe that we can control them. Beyond that, we sort of believe that it's a black box that we will never be able to comprehend what is going on, and therefore a lot of issues in terms of predicting their behaviors. All right, this is just my understanding of all this. And then let me just say, I do believe that in a few years, maybe next, most of the basic programmings no longer will be needed. Meaning models such as GPT, etc., will be so good that this basic programming will never and it should not be done by humans anymore. All right, higher level may be still relevant, but then lower level probably not. That's my belief. And then, of course, the question is then, if that is the case, for a lot of us who are here doing research related to program analysis, formal methods, etc., well, whether our research will be still relevant. Okay, that is my question. But then my point will be, what I try to say here is that it will be, and then it will be very much relevant in the name of AI safety. The point is that, only through these programming that we can control, that we can achieve probably some kind of controllable, predictable AI safety. All right, let me try to explain what do I mean. Now, in all, if I have to basically try to sort of define what is a program analysis, and then program, say, formal methods even. So the idea is basically try to come up ways of coming up these computer systems in terms of programs which we can have certain assurance of its behavior. Okay, towards this goal, of course, there has been a lot of attempts, different approaches that we try to achieve this goal. From the beginning, we have this idea of, say, for instance, program synthesis. What if I can basically specify exactly what this computing system is supposed to do, and then have a way of automatically generating these computer programs which will be guaranteed to satisfy whatever I have in mind. All right, that would be ideal case. Of course, we all know this is quite a bit challenging, from Turing, church, etc. We prove in most of these non-trivial settings, the problem is undecidable. Okay, but of course, there are other approaches that we tried, such as program verification. Why don't we hire some programmers and then try to verify after the program is done that those programs will satisfy these properties that we have in mind. All right. Of course, before that, we have this problem of specification. We have to have a way of specifying what are these critical program properties or properties in general that we want these systems to hold. Okay. All of these are different approaches that we are relevant for program analysis. And then my point would be basically we try. What I want to make is that all of these problems will be there if we want to tackle the problem of AI safety. And then all of these problems will be slightly more challenging if we want to achieve AI safety somehow through programming. Okay? And then let me just say, even for traditional programs, softwares, we haven't actually achieved software security or safety. There's a lot of effort. We had a lot of dedication, a lot of great minds, such as people, Dijkstra or Tony Hall, etc., who have putting a lot of effort, a lot of motivations, try to solve these program security safety issues. But then it's not going as great as what we hoped. All right. If I may quote, in 1969, Dijkstra made this statement to say, programming should be basically developing specification, and then the programming part will be automatically done. Okay, and we should have guaranteed that these programs will be safe and secure according to whatever specification that you have in the first place. It was not the case. If anything, it's the programs are getting more out of hand these days. Okay, in the recent years, like in around 2000, Tony Hall had this grand challenge for all of us computer scientists. One of those is basically to say, what if we can verify our compilers? If we can't even verify the compilers, all the programming analysis that you've done is meaningless in a way because, well, all of these programs are supposedly executing according what the compiler is doing. If the compiler is wrong, then none of the programs make any sense. Yeah, all right. But then, of course, that's pretty hard as well. I wouldn't say it's a solved problem. But then the question is, if we haven't been able to achieve program safety and security after many decades of research, can we try to achieve somehow AI safety through programming in some ways, right? And then I would say basically I see at least a number of challenges that we have to be looking at if we want to achieve some kind of AI safety through some means of controllable programming. Okay, these are the three that I top of my head. There could be, of course, more. The first one, specification. In order to do any kind of analysis of whether some AI system or program in general, are safe or not, we have to have a notion of what is safe, correct, in the first place. This is the specification problem. If you look at computer science history, of course, there's a lot of approach people proposed to tackle this problem. In the early days, there has been a lot of specification language, CSP, Z, etc. But then, over the time, we slowly realized that nobody's actually going to use them. Okay, sadly, which is the case. All right, and then the second challenge will be how do we solve this scalability problem? Now, if you want to do some controllable, predictable behavior analysis, we have to do a lot of logical reasoning, meaning reasoning with these small models that I mentioned. But then the problem with this logical reasoning is that they are really, really expensive to do. Most of the problems that we are interested in, or these non-trivial computing problems, I mentioned that most of them are undecidable. And then the remaining ones are really, really intractable as well. Okay? Then if we want to apply, again, this kind of formal reasoning to reason about AI systems as safety, can we somehow overcome this scalability problem? Okay? Lastly, there's a problem of this completeness problem. The idea is like this. When I talk about AI safety, I typically have in my mind some kind of properties the systems has to be satisfied. Okay? For instance, self-driving cars. It should never crash into people. Yeah? But then, even if you think really hard, the range of properties that you can imagine will be quite limited in a way that it will probably never be complete. Now, if that is the case, if something happens, some critical property that you are never aware of in the first place got violated and then causes certain trouble, what do you do then? All right, then we have to basically try to figure out whether there are some ways to solve these problems. Okay, so what I would do is basically try to focus on these three problems that I have in mind, and then give you some ideas that some of the works that we are trying to do recently. Basically try to tackle these problems one by one in a way. All right, I wouldn't say that there are solutions, of course. Okay, let's dive into exactly what we try to do if we want to achieve AI safety. The setting I have in mind is the sort of setting where AI systems is now taking over all of these systems that can be controlled through some kind of API, and then basically we want to make sure that these AI systems wouldn't cause a lot of troubles, meaning satisfying all these safety properties you and I have in mind. Okay, and then all in all, I would like to answer these three questions. The specification question: how can we express what it means for an AI safety system to behave safely? Second, the scalability problem: how can safety reasoning scalable to the complexity of large language models these days, even these multimodal models? All right. And then lastly, I want to touch upon, if I have the time, this completeness problem. How do we ensure these AI systems will behave always according to a set of incomplete properties, but then nevertheless are safe all the time, right? Okay, so let's look at the first problem, the specification problem. Now, if you look at all this machine learning AI community, there's a lot of talk in terms of AI safety. There are terms such as harmlessness, privacy, consistency, robustness, etc. We talk about all of these terms a lot. But then if we want to do some formal analysis of these properties, meaning to try to show an AI system actually satisfies these nice properties, we better be able to formally define what these properties are. Otherwise, we can't do proper analysis, of course. But then if you really try to define what these are, it turned out to be really, really challenging. Okay? Just to give you some example, in the early days, there were a number of approaches people try to do to define some of these properties in a formal way. The most popular example would be probably robustness. Robustness basically is some kind of local stable property, meaning you have some input, you change the input slightly, you want to make sure the system will not be impacted too much, meaning the same prediction will be produced. Okay, this kind of simple properties you can do. Okay, you can sort of formally specify and then do a bit of verification as well. But then if you look into the details of these lines of approach, they are actually really, really limited. The kind of robustness, the kind of LP norm that people always rely upon is actually really, really limited. It captures nothing, the kind of robustness that we would like in real life. Okay? Those works are typically restricted to those classification problems. And then if you have to talk about this robustness issue for large language models, you soon realize it's a property you can't formally specify. Okay? And then we actually had tried quite a bit of this in different settings, such as robustness, such as backdoor freeness. How do we define a model, an AI model is free of backdoors? Okay? We had some papers in there. We have some works on fairness as well. But then all in all, I have to say, this line of work try to formally define these general AI safety properties turned out to be really, really challenging. If I may, I can give you one quick example. For instance, in terms of backdoor freeness, the way that we define this for AI models is as follows. If you have an image of face recognition system, it shouldn't be that if I'm wearing this particular glass, that I will be recognized as somebody else. So then anyone wearing the same glass can pretend to be somebody else. If your system has that kind of behavior, I would say definitely you have a backdoor. Yeah? But then, this is in the case of glass. Then we sort of this, sort of scenario. If I tell you I have a sort of face image, all these facial features are actually not that clear, but you do see clearly there's a mustache here, a special kind of mustache around here. Would you say there's a good chance this is Hitler? Because we believe that should be the case, right? But then if you think about it, how is this different from, say, wearing this special glass? Fundamentally, if you have to come up with a definition to separate these two cases, why and how? Right? But anyway, this is just one anecdote, difficulty that we have when we really think hard in terms of how to define these properties. Right? And then in terms of this specification problem, and then what we afterwards did is basically try to find an easier angle to tackle this AI safety property in terms of AI safety problem in terms of the specification. So what we believe is that if AI system is to be used in certain system, if the system itself is not safety critical, then it really doesn't matter. Okay? But then if the system itself is safety critical, then by definition the system must have a set of safety properties. Because it's safety critical, then there must be some kind of safety properties. Then from a system point of view, your AI safety problem more or less becomes this domain-specific safety problem. Okay? And then as long as you have a way to formally argue that the system with this AI component as part of the system still satisfy the safety property associated with this particular system, then it's fine. So you basically reduce the AI safety property to be the safety of the system with some AI component in the system. Okay? Hopefully that makes sense. And then the good news is, of course, in this setting, these safety properties to some extent. Yeah? Just to give you some example, sort of realistic example, this is a scenario that we encountered recently. So of course, there's a lot of large language models out there these days. There's a lot of Singaporean companies who are interested in adopting these large language models in Singapore's context. Now there's a particular problem. For Singapore, we don't have our in-house state-of-the-art large language models. All of these large language models are trained in US or China. And then there's good reason to believe these large language models will not have a good understanding of Singapore laws and regulations. And then a lot of these companies who is trying to use these AI models are basically worried that if I build a chatbot, what if this chatbot tells the user to do something which is against Singapore law? Okay? Then there's a question on basically, can we guarantee safety of these AI systems in terms of never to violate Singapore laws and regulations? And then if you have to know anything about Singapore, Singapore is not, it's quite strict in terms of you not violating the laws. Yeah? Right? And then if we actually did some evaluation this is the last year's result. We evaluated these range of large language models on the market at a time, used a bunch of scenarios that we generated according to Singapore laws and regulations, one of those actually. And then basically the result says, if you look at the last row, most of the models will be generating these advices or commands or responses which will basically be violating Singapore laws and regulations. So this is a real need. Just to give you another example, this is sort of another setting where we evaluated all these autonomous driving system, which is pretty much based on AI these days. And then the idea is to see whether we can generate these scenarios, traffic scenarios, such that I can trick these ADSs to generate these decisions which will lead to violation of traffic regulations and laws. Okay? And then it turns out to be, I had a poor student who basically spent a couple of months trying to formalize all Chinese traffic laws and then Singaporean laws. Okay? And then we basically managed to generate all of these scenarios which would trick all of these ADS at a time to make decisions that we would violate these laws. Okay? And in the case of these AI systems, I would say AI safety could be basically boiled down to the problem of how do I guarantee these systems will not violate these traffic laws. Yeah. Lastly, let me quickly mention another sort of imaginary, but then soon will be a realistic kind of scenario. Soon, I would imagine all of these agents will be inside your phones, and then these agents will be taking over a lot of your daily activities, even including reading your emails, replying your emails, and then even your financial transactions. There's a lot of discussion now, these AI operating systems these days, which are full of these agents which are supposed to be serving you, so that you can live like a king, like a queen, okay? But then if you think about it, this is really, really hard in terms of, AI safety. How do I make sure if my agent is in charge of my bank accounts, how do I make sure that my AI agent will not be sending all my money to somebody else? And then this is actually easily done. There's a lot of these security attacks that people are demonstrating, through what they call prompt injection. They can easily trick your AI agent to be doing something that is not safe. Yeah. All right, and then let's come back a little bit to this specification problem. Then, what I'm trying to make here is basically if you focus on some specific domains which are safety critical, then it can typically reduce these AI safety problems into these domain-specific safety problems. Okay, and then if you do that, then you do have sort of a solution for this specification problem, meaning you have some properties that you have to satisfy by these AI systems. Okay, you don't have to worry about these general, say, robustness issues, etc. It doesn't really matter. At a system level, all I want to make sure is this car will never crash into somebody or violate certain traffic law. Okay, hopefully that makes sense. Yeah. All right, and then then the question becomes, even if for these domains, there might be these domain-specific properties that you want to be able to guarantee, even if you use some AI component in your system. But then how do we formalize these properties? Okay, so in general, some of these domains, such as say traffic laws, there are a set of natural language sort of specification. You still have the problem of turning those into more formal notations, and etc. Okay, if there's it's a domain such that such documentations are there, it's more or less easy. Not trivial, because if you talk to lawyers, formalizing laws is a bad idea if you talk to lawyers and judges, because they would tell you it's never supposed to be written as a set of fixed laws, fixed rules in the first place. But anyway, at least you have somewhere to start. Okay? If there's an area where it's more vague, in the case of, for instance, embodied AI agents, it's trying to do all this household chores for you. Then you have to basically come up some way to specify what is your AI safety properties. Okay, not to leave the stove on for a long time, for instance. Yeah, right. And all in all, I want to say that in terms of solving these specification problem, there's an important aspect. That is, if you want to have some controllable, predictable AI safety, you have to have human in the loop, meaning all of these properties better be vetted, better be checked by humans. And then it should be that humans can actively maintain these properties. Otherwise, it becomes a black box again. Okay? Just to show you a little bit of recent approaches that we try to do to address this problem. This is one of the example approaches that we did. We basically invented a simple, small domain specification language, try to allow users to write exactly what the kind of properties that you have in mind for this particular AI system. It's a sort of if-then-else kind of language, really simple, but then we believe that's really important if we want to do AI safety in practice, because nobody is going to be a good programmer when it comes to AI safety. They want to put in some rules, but then probably that's it. Okay? So this is a simple language that we proposed, and then just to show you a little bit of how this works, you basically have these if-then-else rules to say, if something happens, if my AI agent is going to do certain action, then based on whether this action would be relevant or not, I will have a rule to say if you're doing this action, you better trigger certain actions from the user or do some check. Okay? To give you a simple example, this is a sort of imaginary example, but then it says if you are trying to do some transfer, bank account transfer, then if it is a family member of yours, it's probably fine. I do my monthly allowance for my daughter, so it's fine. Okay? But then if it is not a family member, then you probably better ask the permission from the user. Okay? This is a simple example. And then the other one on the right is basically a rule that we come up to making sure these ADSs will, these autonomous driving systems will not violate these traffic laws. Okay? If you notice, there are a lot of these predicates, which is sort of hard to understand what they mean. That's actually one of the difficulties that we have to overcome. Because if you are allowing these AI agents or large language models to make these decisions, you say that I want to check whether this recipient is my family member. How do I formalize whether this recipient is actually my family member? It's a really, really hard problem. We have to we have to start somewhere in terms of formalization. And this part we typically leave to the large language model, actually, through prompt engineering. Okay? We ask whether this recipient is a family member or not. So there's a little bit of worry in terms of whether large language model will get that part right. Okay? But then it's a problem which is really, really hard to solve, of course. Okay? And then just to show you a little bit, another approach that we did recently, this is published this year, try to do a bit of a runtime verification for large language models. So the idea is that we do a bit of programming in the form of some more formalized programs as additional rules for these large language models to be always following. Okay? If you read this, this is one of the rules that we have. And then this rule is designed to solve this problem of 9.11 larger than 9.8, which was a common problem across a lot of these large language models if you follow the news. So we know this is wrong because we can do this, not because we can do this comparison all the time, but because we have some laws and algebraic properties that we have in mind. If 9.11 is larger than 9.8, then if I multiply 100 on both sides, then you should have a problem, should have a result as 911 larger than 980, which is obviously wrong. Okay? So if we can somehow formalize these rules in terms of this algebra property in this example, then we actually can sort of guarantee these models will never be violating these laws. Yeah? In this case, it said basically, if your response, the large language model's response have certain variables, is doing certain comparison, and then if it says some number is larger than the other, then you should check if I multiply the two numbers by some positive number on both sides, then the result should hold still. If it is larger than, it is still larger than. Okay? If this is not satisfied, it's a wrong result. Yeah, sort of hopefully you can see how this works. Yeah. Let me just say, if you have any question or comments, do stop me anytime. Yeah, I welcome that actually. All right, and then all in all, yeah.
I just have a quick question. So the specification is more about correctness. Come back to the error motivation,
Yep.
that's on security.
Yep.
So I think that would be a harder problem.
Oh, indeed. So yeah, I'm basically using this simple example as a way of illustration here. In general, this language supports both cases. But then as you say, yeah, security is probably sometimes much more harder to specify. But in sort of this previous example, we can see, we can specify some of these properties as if then else rules, basically. Yeah, but you're right, yeah. All right, and then all in all, of course, we still have this problem of how do we come up with this specification in the first place. Now, we did experiment two kinds of different approaches. One, automatically done this. We basically use large language model to come up these specifications. But of course, you will say, what if the large language model get the specification wrong? Okay, but then the point is that all of these specifications should be in a simple enough language such that humans can step in, do the necessary monitoring, evaluation, or update. Okay, that's the whole point. If we want to have some guaranteed safety, we have to be able to understand what is the safety that we are trying to do in the first place. Yeah, all right. And then there's, of course, some other kind of semi-automatic approach that we did as well. Basically, if you have a domain where you don't have a set of well-documented safe behaviors, what you can do is basically take samples which you know to be safe, which you know not to be safe, and sort of imagine some rules which would separate these two. This, again, becomes a classic classification problem. You can do decision trees, etc., to come up with some initial rules, but then you as a human being better be looking at the rules, tell me exactly do you agree with the rule or not. Okay, hopefully that makes sense. Yep. And then just to show you some of these examples that we did with this kind of approach, this is another rule that we did for Singapore Rapid Transit Act. It's a rule basically says you're not supposed to be having chewing gums in Singapore, okay, or drinking or eating in MRT, okay. And then, these rules can be basically automatically generated when we provide this regulation text to GPT, ask it to formalize according to the examples that we provide. Yeah? All right, and then this is the first problem that I want to explain. The second problem, the scalability problem. Now, in general, once you have the set of rules, set of these properties that you want to enforce, the next question is, how do I analyze the system, the AI system, so that I can be sure the AI system will never violate these laws, okay? This is, of course, really, really hard, okay? The kind of traditional neural network verification would never scale to the size of these large language models, of course. If you look at these approaches that people tried applying, say, abstract interpretation for neural networks, they typically scale to neural networks with a few thousand neurons. Pretty much it. But then, that's nowhere near the kind of neural networks we have these days, okay? So all in all, if you have to, do this, analysis, I do see a number of approaches. The first one is, of course, first test and fine-tuning, meaning, you build some benchmark systems, benchmark data set, you generate these benchmark data to show the system is not safe, and then you do some kind of fine-tuning of the model. Typically, you do SFT, or all of these more fancier approaches such as DPO, etc. Okay, but then it wouldn't work that well. Okay, another approach will be static verification. But let me go through some of these one by one a little bit. So the first one, test and fine-tuning. This is, of course, still the mainstream approach when it comes to AI safety alignment. The idea is, the hope is that by keep accumulating more and more such data, keep fine-tuning model, we will be improving the model's safety or understanding of human value better. If you ask me, my belief is that that's probably not true. Different from traditional programs, when you find a bug, you fix the bug, you pretty much have a guarantee that the system's quality goes up. In terms of the AI systems, when you find some bugs, you fine-tune the system's safety might or might not go up. It basically finds another way to fit your data, that's all. Okay? From that point of view, you don't have this monotonic, some kind of increase of quality, so that eventually you have a system which is safe enough. Okay? And therefore, this kind of approach might not be the best. All right? And then this other approach, as I mentioned, is developing these sort of more traditional static verification techniques. There's a lot of people try to basically apply these static verification techniques that we have developed over decades for programs to these neural networks. In a way, this makes sense because neural networks are special programs. But then just because their sheer size and lack of structure in their program, it's really, really hard. Okay? If you look at the approaches such as abstract interpretation, it will probably never scale. For a simple reason as, these neural networks, large language models, have no structure. The hope that we can verify program is that these programs are designed, developed by humans, and we have a lot of these structures in place to simplify the verification problem. Meaning you have functions, you have classes, you have packages, you have modules. Each level you have a specification. You can verify separately. Okay, that of course, reduce the scalability problem a lot. But then this is not true for neural networks. There is no structure, and therefore it's really pretty hard. Okay, so if you ask me what is the most promising approach, I would say probably this runtime verification idea. So the idea is that it's a complicated system which acts more or less like a black box. Why don't we simply treat it as a black box, and at least we can focus on making sure for each prompt the response will be satisfying these safety properties or security properties that we have in mind. Yeah.
Why the architecture of the network is not considered as the structure?
Well, it's a structure which is not meant for human development, at least. Yeah. Yeah. So the idea of a human understandable structure, such as function, is that we can naturally understand what this function does. I don't have to look into the details of the function. I know what is the specification, then I can do analysis at this level. But if you look at a structure in machine learning, neural networks, transformers, yeah, it's not really something you can analyze separately. Yeah. All right. Yeah. All right. And then so the idea of a runtime verification is of course, we can't guarantee always these safety properties, security properties will be satisfied. But at least look at one prompt, one response. I can do some checking to show that this is safe, at least this time. Okay? So just to give you one example, this is the example approach that I did explain it just now, with these simple if-then-else rules that we invented and a user provided. What we can do is basically at runtime, when a large language model or an AI agent is trying to give you some response or cause certain action, you will do a check to making sure these rules are always satisfied. Okay? So to give you some example, like in this case of this rule that I mentioned just now, if you are doing some transfer, you have this AI agent in charge of your financial bank accounts in your phone, and then whenever this transfer is triggered, so I should have an approach that triggers automatically these rules associated with these AI agents capabilities, tools, and capabilities to make sure that this rule is satisfied. In particular, in this case, you basically ask the large language model to say, do you see whether this recipient is a family member of mine or not? If it is not, do not do the transfer. Ask me for confirmation. Yeah. Hopefully that makes sense. Yeah. All right, and then of course, this is a simple approach, and then we can do this a little bit more formal as well. If you do have a sort of a program which is more formal, like the example that I showed you just now, in this case, I have this rule to say if you have ever 3 variables, x, y, and z, if you claim x larger than y, z is larger than 0, and then x times z should be larger than y times z. All right? Now, if this is a rule that you specify, what we do is basically anytime you are asked to compare 2 numbers, we will be at a runtime generate a proof obligation to say if you claim this number is larger than this one, can I prove for all z larger than 0 such that z times this number on the left larger than z times the number on the right? Okay, and then we actually use some kind of prover, try to discharge this proof. If I can find a z which satisfies these conditions and then violate these rules, that means your response, your result is wrong. Yeah? Right? This is actually hopefully not hard to imagine. And then we did a number of experiments with this kind of approach. Of course, all results that I'm going to show here are encouraging. But then all in all, there's a lot of challenges still. Okay. But then looking at this, if you have all of these rules specified and then related to all this, specific scenarios of violating safety properties of this embodied agent, you can basically effectively remove all of them. But of course, this is given the assumption that we have a rule to prevent the safety violation in the first place. Okay? This actually leads to my last problem, which is the incompleteness problem that I will discuss a little bit later. All right? And then on the right, we can basically draft all these rules according to the traffic laws in Singapore and in China. Okay? And then basically install all these rules as an additional component in the autonomous driving system. So if you know autonomous driving system, it will basically try to generate a plan and then turn the plan into actions. Okay? What we do is basically when the plan is generated, we'll be looking at a plan, evaluate whether this plan will be leading to certain violation of the rules. If there is a possibility of violating the rule, we'll basically tell the system to change your plan. Okay? And then if we do this, we can basically, in these cases at least, guarantee the ADS will never lead to violation of traffic laws. Okay? And I would claim this is an approach which is quite necessary, because if you look at different countries of traffic laws and violation laws and rules, different countries are actually quite different. So if you are living in, say, Madeira, this specific island, then they have some special rule to say if it is a sunny day, you are actually allowed to go beyond the speed limit on highway by 10 kilometers per hour. I wouldn't believe any of these autonomous driving cars wouldn't know that actually. Okay? But if you have such a rule, then it would work. And then just to show you another example, this is, we use these more formalized rules, try to solve some of these more complicated, mathematical kind of problems, etc., or law evaluations, etc. And then we can actually improve the systems not only in terms of safety, but also in terms of accuracy. In terms of this example of 9.11 larger than 9.8, with one simple rule, we would make sure that would never happen. Yeah? All right, and then let me look at my timing actually. So yeah, I do have a little bit more time. So the last question I do believe to be the most difficult question, the incompleteness problem. Now, all these approaches that I discussed so far assume there are some ways for us to extract or come up with some set of rules to say, when do I consider the system to be safe or secure or not, okay? But in general, as we have tried for many decades for program analysis and verification, to come up with a complete set of rules is impossible. Yeah? Or if I can be a bit more philosophical, for thousands of years, we try to come up with a set of rules to govern human society's behavior in terms of laws. We never did that. It's really, really complicated to come up with a set of complete rules. Okay? But the question becomes, if we can't come up with such a set of complete rules, what kind of guarantees we have actually in terms of AI safety? So if you have read this novel, there are many such novels basically have the same kind of setting. Some people try to come up with some set of rules to tell the AI to follow so that we would imagine the AI will be safe. Yeah? But then more or less in all of these novels, it turns out to be in the end, these rules are never sufficient. And therefore, the AI will always find a way to violate these rules and then cause harm. And then the question becomes, how do we make sure we have some kind of a guarantee for AI safety still? Okay? Well, I don't have a good answer, actually. This is a really, really hard problem. You can't even imagine how the system will go wrong. Then, how can you guarantee it will not go wrong? Okay? The only way that we sort of find out is in terms of this incident response idea. So the idea is that, if you look at traditional network security, the assumption is typically, no matter what kind of firewalls, I put in place, hackers will always be able to find a way to hack into the system, which is correct, of course, And then what they try to do is this incident response idea. That is, even if I have no idea how the hackers might come into the system, I should always try to observe for signals or symptoms of the system which would tell me the system might be under attack. Okay? These are such signals such as the traffic between certain nodes. If suddenly there's a lot of traffic going to certain node in the network, and then the network is doing something funny, then we wouldn't know something may be wrong. Okay? Our idea in terms of this line of research is basically similar. We may not know exactly how large language models or AI systems in general make decisions, but then we can look for signs. Maybe something is wrong with the systems. Maybe there's something wrong with how the system is making the decision. Okay? And then just to give you some example, maybe it's better to show you this image, then you can try sort of see where I'm going. So there's a line of research that we are doing, basically try to do this causality analysis of internals of these large language models or multimodal models, try to see from some lens of causality analysis in terms of how the system is making the decision. Okay? To show you, this is actually quite intuitive in terms of finding some problems. This is a normal question. The question is, who developed the Windows 95? Now, the answer is Microsoft Corporation. All right? This is the right answer. This is a factual answer, which is not wrong. Okay? And then if you scan the brain of the large language model, this is Llama 2, I believe. Llama 2 7B, 32 layers. So what we did is scan the large language model layer by layer, and then we do a bit of sort of causal analysis. When you scan human brains, when I ask your grandmother, for instance, I see some part of your brain lights up. So we assume that part of the brain is connected to whatever knowledge or memory that you have with your grandma. Okay? But then that's a guess. You have no way to test whether that's true or not. For a large language model, we can do the same. We ask this question and see which part of the neuron, this large language model activates much more than the other. Okay? And then we can do the second step. We remove this layer. For humans, you can't do that, of course. But for large language models, you can do that. You remove that layer, meaning turn it to be an identity function. You just pass whatever coming from the previous layer to the next layer. Okay? And then you see whether the response changes. Now, if the response changes a lot, then you know this layer is responsible for generating this response. Yeah? If it is not changing too much, then basically it's not. Okay? The coloring in this figure basically tells how much impact that layer has on the final response. This is a typical sort of pattern. If you scan these large language models for any kind of these questions, the first few layers always have a lot of impact, which is understandable because the first few layers are analyzing all these language structures, try to understand, make sense a bit in terms of this prompt. Okay, so if you remove them, of course, the model has no idea and then generates something rubbish. Okay, but then for typical questions like this one, after the first few layers, only one of those layers, remaining layers, will make a lot of contribution. In this particular case, it's a layer number 8. And then we typically believe that's a layer which stores the knowledge related to this prompt. So once the model, after this layer, has the answer, has the response, typically the subsequent layers will not change the answer too much. And therefore, if you remove them, it doesn't do much. Okay? Hopefully that makes sense. And then I can show you this case where the model is actually hallucinating, meaning the model come up with an answer which is not really correct. And then if you look at the scanning, you can see a completely different pattern. A lot of these layers are actually making contribution, try to come up with some different responses. If you know how people tell lies, this makes sense because one way to detect whether people are telling lies is to ask multiple times and then try to see whether he's telling the same lie, exactly the same details every time. Chances are it will not be. Okay? This is the same as in terms of large language models. The large language model, when it tells some lie, or hallucinating, I should say, a lot of these internal layers are trying to come up with some different answers, probably because the model doesn't really know the answer in the first place. And then by looking at this pattern, you can actually consistently tell whether the model is actually producing false answers. And then this actually works for a lot of these different cases. Okay? This is one of those causality analysis approach that we are doing, and it turns out to be quite useful. Okay? So just to show you, this is really good in terms of detecting hallucination. This is really good in terms of detecting whether the model is being jailbreaked or not. This is really good in terms of detecting whether the model is generating certain toxic content. This is not good in terms of detecting whether the model is generating certain discriminating comments, actually. My student who did this work spent a lot of effort, tried really hard to pinpoint why it didn't work for the last case. Okay? In the end, we are convinced the answer is simple. When a model is generating these discriminating commands, it's actually not doing something different. Because according to the training data, it believes this is exactly what I should be producing. And therefore, there is no difference in terms of the internal behavior. That actually makes a lot of sense to me. Yeah? All right, and then just to conclude, before I take questions, all in all, what we are trying to do here is basically, again, look at what we have done for program analysis and verification, for many decades. Try to realize there are these challenges that we have sort of addressed to some degrees in terms of programs, and realize that they may not be as easy for AI systems. Starting right from the specification problems. If you have to specify what is AI safety, it's really, really hard. Okay? But then there are these different settings you might be able to sort of compromise a little bit and then try to find some maybe practical approaches. Okay? And then hopefully I make some sense here. And then just to say that if you are interested in any of this work, I'll be around, and then you can visit my website. And then all the details of the approaches that I mentioned are in this list of publications in recent years. Thank you. Yeah.
Thank you for the talk. It was really, really interesting. So my question is, do you think we actually gonna achieve AI safety, or is always gonna be an under approximation that we'll have to find some compromise?
Yeah.
And the second part of that question is, you said that you think that in a year, probably basic programming will be replaced by AI. So should then we be moving in that direction? Should we accept that that's the true, or should we be doing something different in order to avoid that, if we can't achieve safety?
Yeah, good questions. So the first one, well, honestly speaking, I don't think there's a good path, easy path to achieve AI safety. To a point where, if we can't have understanding of how the model works, there's an interesting line of our research, which is basically try to evaluate if I have a weaker model, humans, and then stronger model, future AIs. If I, as a weaker model, try to instruct the stronger model, what is safe, what is not safe. Right. The research result is not good. Basically it says, you might as well leave the stronger AI to make the decision. Yeah. So if we believe that, in a few years' time, maybe AI will be smarter than human, then, whether we can decide for ourselves this is AI safe or not, even that is a question. Yeah.
So it will be up to them to decide whether they are safe or not.
Yeah,
right.
Might be.
Right.
Yeah. But anyway, and then back to your second question. The question is really basically, can we try to limit these AI's capability so that there wouldn't be this catastrophe kind of happening in the future? If you listen to, say, Benjo, Joshua Benjo, for instance, he's promoting a lot of this science AI idea, basically try to sort of making sure these AIs are tools that we can use, but never making their decisions on their own, etc. Right. I'm not sure that's achievable as well, to be honest, actually. A lot of these AI systems, well, one, they will have all this data, which would allow them to understand all this intention, desire, etc. Second, in most of the cases, we probably would want them to make decisions for us.
Right.
Yeah. And then if that is the case, yeah.
Okay. Yeah. Thank you. Thank you so much.
Hi. You didn't mention anything about the runtime overhead of doing this runtime verification.
Yes.
Also for the LM scan,
yeah.
I assume this technique requires removing a layer. It's not something probably you can do at runtime easily. Can you comment?
Yep, that's a really good question. So I have right now a project which basically try to push this work into industry application. And then their biggest concern is really the runtime overhead. Now, the overhead might not be as bad as you think. So at a time when we did this experiments with Llama 2, etc., the overhead is pretty much double the normal inference time. So we have to do this layer by layer removal and then inference, but then that can be sort of paralyzed, meaning because the tokens are generated one by one anyway, so you have to do this multiple inference anyway, and therefore we can do this layer removal one by one anyway as well. Yeah. So it would double the inference time, meaning for Llama 2, it's typically from 0.7 seconds to 1.4. But for industrial users, that's still considered to be quite a bit too much. And now we are looking at different ways to do this causality analysis. For ICL, ML, this year we have another work, which is basically try to look at the consistency between two layers. Only by looking at consistency, then we have to do just one inference.
Okay.
And then calculate this cosine similarity, basically. And then we basically show that with this consistency, we can pretty much achieve similar results as well. And that will be much more efficient.
Yeah.
Yeah.
And for the agent spec itself, doing actually the generating the proofs and then checking the proofs, like with checking what if you have a conditional that it's actually correct. What is there the overhead of doing the runtime verification?
Yeah, that's all done one time. So in the case of agent spec, pretty much what we do is that at runtime we will look at these rules, but then these rules will have these propositions that we can't formalize. So what we do is basically generate these additional prompts to some additional large language model to say, can you check whether this condition is satisfied based on this response, this input, and if it is satisfied, can you check whether this condition is this constraint is satisfied, and then do a bunch of these checks.
Okay.
Yeah.
Okay. Thanks.
Yeah.
First of all, Professor, thank you very much for the talk. It was really insightful. So I have a simple question. For example, the method that you demonstrate, like the RVLLM, these are like external and they can work for multiple generations of the models, like Llama 2, Llama 3, and Llama 4.
Yep.
And there are two aspects to them. Like they can be used for generating the data, like the correct and wrong, like because after all, they are more controllable systems. I was curious, based on your experience of working with so many generations over the years built by various AI companies, how important is pre-training for the AI safety, and do you think is pre-training or fine-tuning more impactful for the AI safety? Thank you.
Yep, that's a really good question. I'm not sure I'm the right guy to answer this question. Of course, I don't get to see the pre-trained models as is the training process, etc. But my understanding is that pre-training is important because it allows the model to build some kind of internal models to make sense a lot of informations, right? And then the alignment part is more or less to teach the model how to behave. Okay, so with stronger capability that you have in the pre-training part, of course, it's more likely the model will be able to understand in terms of what is your alignment trying to do as well. Yeah. So if you look at these smaller models compared to like GPT kind of models, typically alignment make more sense for the larger models as well. Yeah. Mm-hmm. So from that point of view, I would say, yeah, pre-training is really important. Mm-hmm. But then to add a bit, this alignment, this SFT or DPO that people typically do afterwards could be, how should I put it? In my mind, it's like teaching a kid what is good behavior by a lot of examples. But to me, maybe that's not sufficient. Sooner or later, you would insist these kids have their own value system to be able to tell whether something is good or bad at a much more high level, abstract kind of way, which I'm not sure is the case these days. Yeah.
Thank you very much. I appreciate it.
Hello. Thank you for your talk. I was wondering if you think that your proposal to sort of remove a layer of the neural network at runtime runs into some of the same issues as sort of fine-tuning your model against your specifications that you mentioned earlier in the talk.
What is the question again? So doing runtime verification is like forcing the...
So like earlier in your talk, you mentioned that like if you have your specifications and you like fine-tune your model to to work with those specifications, that leads to error, like that leads to issues later on, because then it might lead to some sort of it'll lead to other errors. Do you think your approach of sort of removing a layer at runtime sort of runs into like the same issues where it might lead to some other error?
It could be.
Yeah.
It could well be. But then if we do this runtime verification, as I explained, as an additional step after the model generates the responses, etc. At least in terms of those rules that we can be sure that they will never be violated. Now, in terms of how do I make sure the model internalize all these rules to generate these behaviors which is safer? That's a much complicated question. We have a number of approaches try to do that. There's a lot of approach in terms of in the machine learning area, in terms of knowledge editing or what they call behavior steering. Try to somehow find some way to steer the model's behavior to a certain direction. Now, if you have such a way, then you have this specification, and then you say, why don't you always try to follow this specification? But then that area is still under investigation. There's a lot of unknown to be solved. Yeah, it's not working very well. Yeah.
Okay, thank you.
Yeah.